Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Isomers include both structural, constitutional, isomers and stereoisomers, optical and geometric. We must count all distinct isomers of chlorobutane, C4H9Cl. Moving on to the next step. Draw all structural isomers of chlorobutane. Butane has two carbon skeletons, N-butane and isobutane, to methylpropane. For N-butane, CH3, CH2, CH2, CH3, Cl can be placed at C1, 1-chlorobutane, CH3CH to CH to CH to Cl. C2, 2-chlorobutane, CH3CHClCH to CH3. These are the only unique positions due to symmetry. For isobutane, CH3, 3CH, Cl can be placed at C1 on a methyl group 1-chloro-2-methylpropane, CH3 to CHCH to Cl. C2 on the central carbon 2-chloro-2-methylpropane, CH3, 3CCl. So there are 4 structural isomers total. Moving on to the next step. Check for stereoisomers. 1-chlorobutane, no chiral center, no stereoisomers. 2-chlorobutane, C2 is a chiral center, attached to H, Cl, CH3, CH to CH3, all 4 different. This gives 2 enantiomers, R and S. So this adds 1 additional stereoisomer. The pair counts as 2 isomers, but we already counted 1 structure, so we add 1 more. 1-chloro-2-methylpropane, no chiral center. 2-chloro-2-methylpropane, no chiral center, C2 has 3 identical CH3 groups. And for the final step, total count. 4 structural isomers plus 1 additional enantiomer for 2-chlorobutane is equal to 5 total isomers. Why other options fail? A. 2 counts only some structural isomers, ignores stereoisomers. B. 4 counts only structural isomers, ignores optical isomers of 2-chlorobutane. C. 6 overcounts, there is only 1 chiral center producing 1 pair of enantiomers. Therefore, the correct answer is D. Therefore, the correct answer is option D.